All right, so what do we do with all the specific heat, stuff that we've been talking about? How does that fit into the grand scheme of trying to figure out heat change in a process in the lab? Let's look at some examples. So we're going to look at some physical examples and then some chemistry examples. So example 10 talks about a physical example using a calorimeter. Excuse me. Okay, so let's read this together, then we'll start to break it down. A 30.4 gram piece of unknown metal is heated up in a hot bath to a temperature of 92.4 degrees Celsius. Whew, hot. The metal is then placed in a calorimeter that's containing 100 grams of water at 25 degrees Celsius, about room temperature. After the calorimeter is capped, the temperature of the calorimeter raises, I don't know, to 27.2 degrees Celsius. What is the specific heat of the unknown metal? Assume the calorimeter does not absorb heat. Okay, that's a lot going on, right? We got a heck of a lot happening here. So we really need to break some stuff down and explain it before we actually start doing any sort of calculations. Okay, remember a calorimeter is insulated. So no heat's going in, no heat's leaving, theoretically. Okay, so when you put a hot piece of metal in an insulated calorimeter that has water in there, okay? Remember, thermal energy is always going to go from hot things to cold things. So the thermal energy is radiating out of the hot metal, and it's being absorbed by actually two things. It's being absorbed by the water, but it's also actually being absorbed a little bit by the material that makes up the calorimeter itself. Styrofoam, for example, if we're doing the coffee cup calorimeter. So another way to think about it, the heat that the metal is releasing, that's why it's negative, is equal to the heat that is being absorbed, that's why it's positive, by the water, and also the heat that's absorbed by the calorimeter itself. Okay. Now this value, that the amount of heat that the calorimeter absorbs is so small that usually it can be ignored. And so unless the problem tells you otherwise, we can basically remove that. So a simplified version is that the amount of heat that the metal is releasing is equal to the amount of heat that the water is gaining. And this supports or backs up the first law of thermodynamics, or the law of conservation of energy. You can't produce, or you can't create or destroy energy, it just gets transferred. So if the metal is losing energy, what's absorbing it? The water. Now how is that going to help us? Well, we have a lot of stuff going on here, right? So let me do this. Over here, I'm going to make two columns. I'm going to make one for the metal, and I'm going to make one for the water. We're going to write down what we know about each. All right, so for the metal, I know its mass is 30.4 grams, right? What's the mass of the water? Do I know the mass of the water? Yes, it's 100 grams. All right, do we know the specific heat for the metal? No, that's actually what we're solving for. But do we know the specific heat of water? Well, remember, it doesn't tell us, but we should know what that one is. It's 4.184 joules per gram degrees Celsius. All right. Do we know the delta T for the metal and for the water? Well, it doesn't explicitly tell us. It doesn't say, like, the change in temperature is this. That'd be too easy, right? But it does give us some temperatures here. And actually, let me do this. Instead of doing delta T, I'm actually going to put this. Okay, the initial temperature and then the final temperature. And then same thing for the water. What's the initial? What's the final? And then from those values, we can obviously figure out what the change is. Okay. It tells me the metal, let's see, it's heated up, the metal is heated up in a hot bath to a temperature of 92.4 degrees Celsius, and then it's placed in the calorimeter. The initial temperature is always what's the temperature of the metal right as it's going into the calorimeter. So if the metal is heated up in a hot bath to 92.4 and then transferred into the calorimeter, the initial temperature for the metal is the 92.4. So it's that hot piece of metal right before it goes into the calorimeter. Now, once it goes into the calorimeter, we're told that well, hold on, let me actually pause on that. So that's the initial temperature for the metal. What's the initial temperature for the water before the metal was added? It's 25.0 degrees Celsius, right? So 25.0 is the initial temperature there. Now, what's the final temperature? Well, here's the thing. We are told that the calorimeter, once it's capped, the temperature ends up reaching 27.2. That's the max temperature of the calorimeter. So the 27.2 degrees Celsius, is that the final temperature for the water, or is that the final temperature for the metal? Well, here's the thing. It's both, right? Because they've reached thermal equilibrium, right? So the metal is going to keep releasing energy until the water and the metal become the same temperature. Once they're the same temperature, there's no longer a hot object and a cold object. They're both the same. So there's no transfer of thermal energy. So the final temperature is actually the same for both. It's 27.2 degrees Celsius. So you can see without doing any math, what happened to the metal? Its temperature went down. What happened to the water? Its temperature went up. Why? Because the metal's losing energy, the water is gaining energy. Okay, with all that being said, we need to figure out what the specific heat of the metal is. So I'm going to expand this out a little bit. So negative Q of the metal is equal to positive Q of the water. Well, what does Q equal? Well, remember we saw in previous videos, Q is mass times specific heat times delta T, right? So here we go. It's going to look really long, but let's expand out. So negative, what is Q? Q is mass times specific heat times, I'm going to put T final minus T initial. Now that's all for the metal, equal, what's Q over here for the water? Well, Q also is M times S times delta T, which is T final minus T initial. Okay, the thing is though, everything that's on the left side, all of this is for the metal. And everything that's on the right side is all for the water. So it's going to look a little wonky and a little crazy, but just take it slow. So negative, what's the mass of the metal? 30.4 grams. Times specific heat, that's actually what we're solving for. We don't know what the specific heat is of the metal. Times, final temperature is 27.2 degrees Celsius minus the initial temperature was 92.4. Okay, so that's my metal. That's equal to, now everything on the right side is the water. So what was the mass of the water? 100 grams times the specific heat, 4.184 joules per gram degrees Celsius. And then times my final temperature, 27.2, minus the initial 25.0. Try not to run out of space. Okay, so heck of a lot of numbers, right? Let's do a little bit of cleanup. Let's make this look a little nicer. Okay. So first thing I'm going to do is these subtractions. Let's figure out what those are. So for the metal, okay, so for this right here, 27.2 minus 92.4. This is going to be, with my correct sig figs for subtraction, 1 decimal place, this is going to end up being negative 65.2. That's the change in temperature for the metal. What about the water over here? I don't even need to calculate that one. The water is going to be positive 2.2 degrees Celsius. It went up by that much. Okay, so now I can go ahead and start to do my multiplying. Let me just do a different color here. Okay, so the water side, there's no unknowns on the water side. So let's multiply all that together. So the mass is 100 grams times the specific heat is 4.184 times, we just figured out that the change in temperature is 2.2. Okay, so that ends up being 920.48, and it would end up being joules. because the grams cancel and the Celsius cancels. I'm not doing anything with sig figs yet. We'll wait till the very end. So 920.48 is just what I get when I multiply all that. Now that's equal to, on this side, we have negative, I'm going to take the 30.4, and I'm going to multiply it by the negative 65.2. So we have the negative on the outside, but then 30.4 times negative 65.2 is negative, let's see, 1982.08, and then times S, right? Because we still have S in there. That's what we're trying to solve for, okay? So let's go ahead now and isolate what S is. Okay, so I'm going to take 920.48 divided by, these two negatives are going to end up canceling each other out and making it positive. So divided by positive 1982.08, my specific heat, my S value, is 0.46, and it's joules per gram degrees Celsius. Okay, because I was really bad over here. I wasn't retaining sig figs on this side very well. That's my bad. It was getting a little messy. But specific heat is always joules per gram degrees Celsius. Now, why did I do 2 sig figs here, right? Well, when I started multiplying and dividing, my answer needs to be in lowest sig figs, right? So we had 3 sig figs here, 3 sig figs here, 3 sig figs here, because that decimal makes it 3. 4.184 is 4, and that's actually an exact number. But here's the lowest, 2.2, right? So 2.2 is the lowest, it's 2 sig figs. That's why ultimately at the very end, I made my answer 2 sig figs. All right, this problem right here, example 11, is essentially the exact same thing, just different numbers. So here's what I'm going to do. I'm not going to work this one out, but I am going to let you solve it. Pause the video. When you want to know the answer, just hit play and it will be on the screen. All right, I went ahead and put the work out on the screen. I didn't go into the level of detail that I did in the last video, but I've got all the numbers plugged in where they need to go. Your delta T's for the metal as well as your water are here. You should have ended up getting for the specific heat for the metal 0.829 joules per gram degree Celsius. Notice 3 sig figs here because your lowest sig figs, if you look at all of your numbers, the lowest is 3 this time. So always be making sure you're watching out for those sig figs. But if you understand the concept of what we're doing in these problems, that's the important piece. That's really what I care about. Okay. The rest of this section, section 4, talks about how you would do the same idea, but with a chemical reaction. And to be completely honest with how fast we're moving in this semester, we are not going to cover the chemical examples of calorimetry in this particular semester. So don't worry about having to teach yourself the chemical example. If you are curious as to how to do that, you can certainly reach out to me. But Chem 152, we will pick back up on that, and they'll teach you how to do the chemical examples. But for just how much we have to fit into this semester, just with everything going on, I'm not going to make you do the chemical examples, all right? So that wraps up this section, which is the calorimetry section. So I'll see you in the next section, which is Hess's Law.